Welcome to another video in our series Demystifying 5G. So the last time we talked about some of the limitations that LTE has using OFDM as a waveform. And I'm still here with my setup, and I'm generating a 20 megahertz LTE signal, as you can see on the spectrum analyzer. And what I would like to do is smooth out the trace a little bit. So what I'm basically doing is I'm choosing trace here, and instead of clear right, I would like to do the max hold, and I set the detector type to RMS. And as soon as you see that, we see the characteristic skirt that is called typically here in the power spectrum that LTE provides. Right now I don't do any time windowing, which I showed you the last time. That smoothed out the spectrum, but that introduced that artificial intersymbol interference and made the EVM worse. This is the kind of worst case view that you basically get. So you see the skirt here. Of course, that would require a guard band so that you don't harm any other adjacent system or other LTE carriers. So 5G is tackling that with discussing some new waveform candidates. So let's compare them. So what I will do first is to keep that trace. I choose trace again, and I will put on view. And then I choose a second trace and put it on clear and write. So you see here now, if I close that window, you see my LTE spectrum shape here in yellow and my new trace in blue. So now I'm switching back to the signal generator, because on the signal generator, the SMW 200A, ROHDE&SCHWARZ implemented 5G waveform candidates. So let's take a look. So I'm choosing baseband, and in baseband you can see here LTE, but right beneath it you see the 5G candidates. While doing so, we enter the personality for the 5G air interface candidates, and if you choose here modulation type, you see right now UFMC, but if you open up you see that ROHDE&SCHWARZ implemented 4 of these 5G waveform candidates. So UFMC is the first, which stands for Universal Filter Multicarrier. We also do have GFDM, Generalized Frequency Division Multiplex. We have FBMC, Filter Bank Multicarrier, and we have filtered OFDM. So let's go in here. Let's choose for as an exercise here UFMC, and I would just like activate that signal here. So it's now already been activated. If we choose general settings, you see here you can define the total number of subcarriers, the subcarrier spacing, with or without cyclic prefix, symbol length, occupied number of subcarriers, and so forth. And then some specific characteristic that's part of UFMC. It's using a Dolph-Chebyshev filter type to filter a number of subcarriers, so to speak. So we take that entire bandwidth, and it will be divided up into subbands, and that filter and these filter settings that I can apply here in the generator will be applied to that subband definition. So if we're coming back here, you see a filter length can be defined, stop band attenuation, and then of course last but not least you can define the number of subbands, and that will of course relate to a certain number of subcarriers per subband as it is defined in UFMC. So all this is possible, gives you quite some flexibility here. The same things would apply if we choose now filter bank multicarrier, GFDM or filtered OFDM. Not exactly the same settings, but kind of in a similar way. Because these 5G waveform candidates, what they all do is they're applying a certain defined pulse shaping filter mechanism to overcome these spectral characteristic that OFDM provides. So let's take a look at UFMC on the spectrum analyzer side and see how it compares to LTE. So as you can see, the spectrum shape here for UFMC, right, displayed on the screen is of course different than what LTE offers. So if we take a closer look and also apply now the same trace settings for UFMC, we can pick max hold and we choose RMS as a detector and close this up. You can easily see here the much sharper spectrum edges. Why is my signal a little wider? Because I didn't make sure that I'm exactly matching the LTE settings and parameterization. So that's obvious here. But the much sharper edges of the spectrum come of course by that filter settings that we have applied while creating a UFMC signal. You also can see here the number of subbands in the spectrum shape. That is something that I just picked to visualize these effects. But clearly the goal that these waveforms have to have a better spectrum agility than LTE is fulfilled in this particular case. And what is it good for? Well, if there's power amplifier design companies out there that want to make sure that their amplifiers also support these kind of new waveform schemes that are being discussed right now in the industry, they could utilize this setup, they could utilize the signal generator to generate these signals, to play with the parameterization, probably a little bit better than I did. And then of course use the analyzer to do power amplifier specific measurements, measure AM to AM, AM to PM curves, measure the CCDF to get a sense about the crest factor, the peak to average power ratio, and all these kind of stuff. Thanks for watching, and I hope you enjoyed our little excursus to 5G waveform candidates.